Okay, let's go. It's test time, and I'm doing the option test, and I'm doing tick option B, human musculoskeletal anatomy. So I can ignore all this nonsense about the immune system. So here we go. In 1953, Huxley introduced the sliding filament theory. So that's the one that you were taught to explain muscle contraction. This theory was based on the idea that muscle proteins slide past each other to generate tension. Below is a diagram of two sarcomeres. So here we've got the I band and the A band. And absolutely delightfully, the artist has drawn the two types of protein, different thicknesses. So this thick band is myosin, and this thin band is actin, and the A band contains both of those. So A band, actin and myosin, I band, just the thin actin filaments. And then we come to these other two lovely proteins, troponin and tropomyosin. Now I'm sure that if you think back, you will to the beginning of sliding filament theory, as you're sort of going through this, you'll be thinking, calcium ions diffuse from the sarcoplasmic reticulum and they bind to troponin. And all you need to do then is decide, well, where is the troponin? It's on the actin because it moves the tropomyosin so that the cross bridges can form. So anywhere we've got actin, we are also going to have troponin and tropomyosin. So A band has got actin, I band has got actin. Super duper 2 easy marks. And pretty much AO1. So, trigger words, explain. So we've got to give it a, explain how. Explain how. Say what happens. The interaction between actin and myosin results in the contraction of the muscle. And it says we don't need roles of troponin and tropomyosin. So we don't need to start off with that calcium ion thing. So what they really want us to do is talk about cross bridge formation, and then the contraction bit. That's when those myosin heads move and pull the actin fibres. So remember, we've got this sort of linking on, doing the power stroke and moving the actin that way. So remember, this is your paper, you can draw on it, it's okay. So cross bridges form between actin, I'm going to put binding sites there, I think that's better, and binding sites and myosin heads. The myosin heads bend to slide the actin over the myosin in contraction. And quite a lot of you put something about the power stroke there, and that was all to the good. So that's page 1, pretty much AO2 stuff. And then we've got a graph. No, we don't like a graph. I don't like a graph. It looks horrible. I've never seen that graph before. Horrid. So, muscle samples can be analysed to produce a length tension curve. How lovely. What's that then? So, we've got tension up the side. So, remember it said it's the contraction generates tension. So, this probably represents some kind of contraction. And then we've got the sarcomere starting length in micrometers. So it tells us some details of what they've done. We suspend the muscle fibres. We position them so that they're at different lengths, A, B, C. Muscle fibres are stimulated to contract. The tension force generated as a percentage of the maximum is measured at each sarcomere length. Still don't get it. Anyway, the results are shown on the graph. Diagrams of sarcomeres are not drawn to scale. That's quite important. So we can't do any measuring off the graph, that's what it's telling us. We can't measure these fibres. So, to determine the length of sarcomeres at different resting positions, myofibrils were viewed down a high-power microscope. Muscle proteins were stained using fluorescent chemicals that bonded to actin and myosin, so we can distinguish. Explain why at least 20 sarcomeres were measured. So this is the old reliability question, isn't it? Why do 20? Why not just do 1? Which would be a lot easier. So, measuring 20 improves reliability as an average can be calculated. And I think I'd be always tempted, if I'm talking about averages, to reduce the effect of anomalies. I do like that. Reducing the effect of anomalies. It means if you've got one that's a bit weird, it doesn't affect your data. Okay, so use the graph. Oh, who would want to? Use the graph to calculate the length of the actin. So we only want the actin fibre, not the whole sarcomere, just the actin. So now we've got to look at what's going on at the graph, because so far we've not had to. So here we go. This is the muscle. So this one, I'm going to do a bit of annotation on it, is fully stretched. There's no overlap between actin and myosin. Here it's contracted, but we can't, so there's a bit of a gap there, isn't there, between the two actin fibres, so I think that's probably not going to be terribly useful. But here, this one is fully contracted. And if we look at the diagram, we've got myosin there and there. So this one is going to give us the length of the myosin alone. So that will give us that length. And then what's left in this one is the actin. And we've got sort of one over here and one over there. I'll call them A and B. So in fact, if we have the difference between that length and that length, that will give us A plus B. So if we do big C minus big A, that will give us A plus B, and then we can we want to know the length of A, which will be A plus B over 2, is what I'm thinking. So we've got two sets of actin fibres. So what are our numbers then? Gosh, this graph paper's rubbish, isn't it? I make that to be 1.2 micrometers, and this one to be that's 3.5, 3.6 micrometers. So I'm going to do 3.6 minus 1.2 equals 2 times the actin fibres. So that's 4.4, no, 4.4, where? 2.4, 2.4, 2.4. See, I can't do maths, I should have used the calculator. That's why I've got one. I have got one, I'll just prove it. There, it's there. So two actin fibres equals 2.4 micrometers, always put your units in. So one actin fibre equals 2.4 micrometers divided by 2, 1.2 put your units in, micrometers. Now actually randomly there was another way of getting to that answer. So some people just kind of went, what's that number there? I'm going to choose that one. So by randomly choosing one of 3 points off the graph, got to the right answer, which was interesting. And some people chose over here and went, oh, that's 2.4, it'd be half of that. Don't quite know how that would work, but anyway. So, physiologists conducting these experiments use tissue from the same organism. Suggest 2 other factors that would need to be controlled. Now my all-time favourite factor to control when carrying out an investigation, and I'm just going to check over here, doesn't say anything, suspended, positioned, contracted, measured. Nothing about temperature. Fantastic, I'll control that then. So, temperature, it's protein, how about pH? And, really, sometimes they're only worth one, they'll only accept one of those. So what else would we need? Use the same muscle type. If you're going to take it from the leg, always take it from the leg. Suggest, I like that. An explanation as to why no tension is generated at C. So what do we say at C? C, fully stretched, no overlap, no cross bridges. And we said here that the contraction generating the tension was because of cross bridges and the myosin heads moving the actin. So the myosin heads are not forming cross bridges because the actin and myosin are not overlapping. Okay, that's gone on quite a long time. I'm going to do a different one on joints. Join me later.